So now moving on to chapter 9.2. So far we have been thinking about two populations and comparing their population means, and we've done case 1 and case 2 so far. That was everything from 9.2, and we talked about both hypothesis testing and confidence intervals for case 1 and case 2. So this was both in 9.1. Now here in 9.2, we are going to move on to case 3. So all of these cases are directly analogous to the corresponding cases when we are talking about a single population from which we are trying to do inference on the population mean itself, the one population mean. Here, we're in case 3, and if you'll recall, what that meant back when we were talking about a single population was that the assumption was, so we had this assumption that the samples are drawn from normal populations. So that's important. So let me write this. Case 3, samples are drawn from normal populations. So in the previous setup where we had one population, or one sample was drawn from a normal population. Here we have two samples that are drawn from a normal population. The other thing, excuse me, is that the two samples must be independent of each other. So again, that's really important. We have to have samples that are independent of each other. They can't have a relationship to each other, and we will definitely be talking about when we have samples that are related to each other later on. The other things that we need for case 3 are unknown sigma 1 and sigma 2, so we don't know what the true population standard deviations are. And this is going to be for small sample size. Because if we had a large sample size, then we could just use case 2, the z-test there. But for a small sample size and for unknown sigma 1 and sigma 2, we need to use case 3. All right, so let's look at this theorem here. This is just giving you a little bit of kind of preliminary theory here upon which we build our confidence intervals and hypothesis tests, right? So all this is saying is that if you have this x bar minus y bar quantity, and you're thinking of that as an estimate for mu1 minus mu2, but if you take x bar minus y bar and you subtract off the mean of x bar minus y bar, which is this, okay, and suppose you know them and you're able to subtract them, and then you divide by the standard error, the estimated standard error, because you don't really know the true population standard deviations. So when you're doing these standard deviations of x bar minus y bar, then it's an estimate. But the point is, you are taking x bar minus y bar, you're subtracting off its mean, you're dividing by its standard error. And when you do that, if you knew everything in this expression here, this whole thing would be distributed as t with a particular degrees of freedom. And that degrees of freedom is here. Okay? So this is just showing you that we know something about x bar, about the distribution of x bar minus y bar, if we know the true values of the population means. If we know the true difference, mu1 minus mu2, then we know how this thing is distributed. And that is what allows us to do our hypothesis tests and make our confidence intervals. So this is a much more complicated formula for the degrees of freedom than we had when we had just one population. And it turns out it is kind of a sticky, a tricky kind of problem to to know the degrees of freedom when we have two populations like this. But there's a number of different ways of estimating what the degrees of freedom should be. But here we have the one that your book uses, and it's complicated. I just wanted to show you guys, this is in two parts, so they're expressing it in two different ways. This side here is probably what is going to be more helpful to you, a more helpful form for your homework. Okay, so when you're doing the homework, a lot of times they're going to be like straight up giving you the standard error of the two different sample means, as you see here. And if they give you those, then all you have to do is plug into this formula like you see there to get the degrees of freedom. So you'll need those degrees of freedom when you are doing the hypothesis testing. So speaking of hypothesis testing, here is what it looks like for the two-sample t-test. This all is pretty familiar, okay? You have the parameter of interest, mu1 minus mu2, equal to the null value. As I've said, this null value here, when we're talking about two populations in this course, our null value is typically going to be 0. It can be other things, but we're going to be using 0 usually. The test statistic has the form that you see there, which is the observed x bar minus y bar, and then you subtract off the null value and divide by the standard error. And that test statistic under the null hypothesis should be distributed as t. The only thing that you don't know about the distribution immediately is the degrees of freedom, and that is something that you have to look up when you're determining your p-value. You can see in the p-value determination here, you need to know the degrees of freedom in your t-distribution, and that you're going to get by using the formula on the previous page. So let me just back up here. You guys can see the degrees of freedom is something you're going to have to calculate using all the sample quantities that you have. Okay, so once you have determined your degrees of freedom, then you can use this p-value determination table to decide whether you are what your p-value is. And of course, as always, the row of this table that you use depends on what the alternative hypothesis looks like. So here's an example problem. We're talking about a flexible liner that they thread through municipal pipelines. And it's talking about the tensile strength of these liners, okay? And we have two different processes that get used to make the liners. So we have a fusion process, a sample of liners that had the fusion process. There's a sample that did not have the fusion process. And we are interested in knowing, it says, assuming the distributions of the tensile strengths are normally distributed, perform a test to determine whether the average tensile strength is greater for the liner specimens with the fusion process than without. That's what we're trying to figure out here. So that's important that you really focus on what the question is actually asking, because that is going to inform your alternative hypothesis. And the hypotheses are just marginally trickier to write in the two population situation, because you have to think about which population you're saying you think might be, or you're trying to show has a larger mean. And that's going to determine what your alternative hypothesis looks like. So let me just show you guys this data that we have here. It shows the individual values for each group, right? But then it also just gives you right here the information that you need for calculating the test statistic for this two-sample t-test. So keeping the same data here, and I'm just going to walk us through the steps here. So first of all, I want to start by just like labeling my populations, okay? This first one has a population mean of mu1. I can tell that because I'm calling this S1, so the corresponding mu is mu1 I'm just trying to keep things consistent here. This one has a population mean of mu2. So the parameter of interest is going to be mu1 minus mu2. That's not surprising. That's how it always is. Now the question is, how do I formulate my alternative and my null hypotheses? So I think it's sometimes useful to start with the alternative hypothesis, because the alternative hypothesis should line up with whatever claim or research question is being asked. So here I rewrote the research question up here. Perform a test to determine whether the average tensile strength is greater for liner specimens with the fusion process than without. So what they're saying is, remember, with the fusion process is, this is mu2. The average for with the fusion process is mu2. The average without is mu1, according to what I wrote on the table here. And so they're basically saying, is it true that mu2 is greater than mu1? Okay, that's the question. That's the research question. But we can't write our alternative hypothesis in that way. We're going to write it as, we're going to move the mu1 across to the other side. Or I'll use move the mu2 across to the other side, so it's mu1 minus mu2. So it's really 0 greater than mu1 minus mu2, right? It's the same thing as the line above it. I just I subtracted mu2 from both sides. And so now I have something that looks like what I need. I need my parameter of interest, mu1 minus mu2, and I need to have it in some relationship with the null value. So really, the null hypothesis here, I can turn this around and write mu1 minus mu2 is less than 0. I just turned around the inequality. That's how I like to see it. So now the null hypothesis is mu1 minus mu2 equals 0. Okay, so I have my null and alternative hypothesis right now. Now we're writing out the test statistic. This is just the formula that we're given for the test statistic for the 2-sample t-test. It looks like this. Not minus 0, minus the null value over S2 squared over M. Okay, oops, I wrote those in the wrong order. This is M, this is N. Okay, now that I've got that, I'm going to plug in my X bar, my Y bar, M, N, S1, S2. So this is 2902.8 minus 3108.1. The null value, hey, the null value is here. Delta naught, it's 0. I'm going to just leave it off. Divide by 277.3 squared over 10 plus 205.9 squared over 8. And this is minus 1.8. So we now have to find the area. We have to determine the p-value. So looking at the alternative hypothesis has a less than in it. So looking back at how I do my p-value determination, this is the part I want. I want the area under the t curve with the correct degrees of freedom to the left of t. So just remember, the t-table doesn't give you left tail probabilities, it gives you right tail probabilities. So whatever we look up in the table, we have to do some subtraction to make it work to find the area to the left of t. So we need the area to the left of minus 1.8 under t with a particular degrees of freedom. the degrees of freedom we're going to get by going back to that formula. And I'm just going to put a little star next to the formula. This is the degrees of freedom formula for the two-sample t-test. Putting a star here. It's too much for me to rewrite out each time. So remember, when you're getting the degrees of freedom for the two-sample t-test, we're going to get, using this star formula, we're going to get the degrees of freedom. And I calculated it to be 15.94. We should round down for degrees of freedom. So we're going to go down to 15. And now we'll go to the table. So just look at the table with me. We're wanting the area to the left of minus 1.8, but the t-table here, there are no negative values, okay? The t-table is only going to show you the area to the right of particular values, and those values are going to be positive values. So there's a couple of ways to get what you want here. If you want the area to the left of a negative value, minus 1.8, well, I would say the best way to do this would just be to get the area to the right of the positive version of this, because it's a symmetric table. So you want this. So minus 1.18 is here. You're looking for this probability. You might, since you have right tail probabilities only in this table, just go to 1.18 and get this probability here. And that's going to be the same as what you're looking for on the other side. So this area to the left of minus 1.8. Oh, sorry guys. I put 1.18 down here. I meant 1.8. Okay. The area to the left of minus 1.8 equals the area to the right of 1.8, which equals, let's go and see. We calculated the degrees of freedom to be 15-ish. 1.8 is here, so the intersection is this 0.046. So the area to the right of 1.8 is 0.046. That's the same thing as the area to the left of minus 1.8. So now we have our p-value. So the p-value equals 0.046. And the idea there is we're trying to see how extreme was minus 1.8 in the direction of the alternative hypothesis. So we consider minus 1.8 to be extreme. How extreme? Well, you calculate the probability of everything as or more extreme as minus 1.8. And that's just going to be everything in that left tail, which gives us a probability of 0.046. Last step here then is to do the comparison between P and alpha. So we have I'll write it up here actually, the p-value equals 0.046, which is less than 0.05, which is the typical alpha that we use. I don't believe an alpha was specified in this problem. It wasn't. So when it's not, we'll just use alpha equals 0.05. And because the p is smaller than alpha, that means we reject the null hypothesis. That means, since the null hypothesis, just go back and check, the null hypothesis was mu1 minus mu2 equals 0. And the alternative was that mu1 minus mu2 is less than 0, which we worked out is the same thing as saying that the average tensile strength is greater with the fusion process than without. So we have evidence that the average tensile strength is greater with the fusion process than without. That's our conclusion here. All right, the very last thing I want to show you guys is the corresponding confidence interval. So in all of these, we're still living in case 3, okay? Still case 3. All of these cases have both a hypothesis test and a confidence interval. Here's the confidence interval, and it's just created by kind of rearranging the things in the hypothesis test. And you can see we have in this sample problem basically everything we need. We've got our X bar, we've got our Y bar, we've got, oh, sorry, that's not X bar and Y bar. That's M and N, and there's X bar, there's Y bar, sample standard deviation, so S1, S2. So that's almost everything that you have to plug in. The only thing that you don't have is this T. This critical value, you're going to calculate not using the table we were just looking at. The table we were just looking at is A.8, and that's useful for hypothesis testing. For confidence intervals based on T, you're going to want to use A5. Okay, that's the one that gives you critical values corresponding to particular probabilities, okay, in the tail. So you're going to calculate the degrees of freedom from, so you really have to use table A5 and calculate degrees of freedom using the formula, the starred formula from the previous pages. Okay, so once you get the degrees of freedom, your alpha on this problem is not given. We're not given a particular confidence level that we are trying to achieve because it doesn't actually mention the confidence interval in this text. So if our alpha, if it's a confidence level of, just as a reminder of how these guys work together, if it's a 95% confidence interval, then that means alpha is 0.05. That means alpha over 2 is 0.025. So you've got all the pieces that you need with this and the degrees of freedom to get T from table 8.5. You plug in everything and you have a confidence interval for the 2 sample T test. And that is it for today. Next, the next thing will be on a paired T test, which we'll get to next class.